Welcome to our video about area monitoring. In the first part, we will look at what an area monitor is and why it is sensible to use an area monitor. In the second part, we will see how an area monitor system is realized and what the main differences are between a broadband and a selective monitor. Part 3 describes the broadband area monitor Narda 8059 in more detail with its features and probes. Part 4 takes a closer look at the selective area monitor 8061. Part 5 is about the use of mobile area monitors. Part 6 presents reference installations around the world. Part 7 is a summary of everything so far. Finally, the Annex contains some ideas on how to find a suitable location for setting up an area monitor and some information about the AMS 8063. So back to the question, what is an area monitor? An area monitor monitors the field strength of electromagnetic fields, such as those produced by broadcast and cellular network antennas, as well as power lines and many other applications. Legal limit values have been set around the world for these so-called non-ionizing fields, sometimes called electrosmog. An area monitor permanently monitors adherence to these limit values. Additionally, the measured values can be posted on the internet so that, for example, local residents can check the actual exposure level at any time. It is also possible to initiate an alarm wherever a threshold value is exceeded. At last, since the Dieselgate scandal, it has become clear that it is better to verify than to trust. So why area monitoring? Years ago, the only common source of high-frequency radiation were broadcasting transmitters. But these were mostly sited well away from urban areas, and the antennas were high up on masts and therefore out of reach. Cellular communication networks have brought the base station antennas right up to our front doors. Nowhere near as big or powerful as a broadcast antenna, but in our neighborhood and in plain view. And the demand for more and more wireless services, higher bandwidth and constant availability means that more and more stations are being installed and there is no end in sight to this development. The numbers are constantly rising, as the ITU diagram clearly shows. The ITU gives pause for thought. Electromagnetic fields are imperceptible and unknown for the general public. This unawareness and imperceptibility generates distrust and rejection among the population, which can result in social conflicts and lead to delays in the deployment of new wireless technologies. Operators and authorities are therefore faced with growing protest against the installation of base stations. Operators can be faced with considerable extra expense caused by delays and legal challenges. The purpose of an area monitor network is to objectify these often emotional discussions. The arising radiation is permanently checked by the area monitor network and the measurement values are recorded and published. This transparency serves to build trust among those who live close to the transmitter stations. Realization of an area monitor network. The sensors are preferably placed at locations that are of public interest, such as marketplaces, schools, kindergartens, retirement homes, and so on. The monitors operate completely autonomously and periodically transmit their results to a central server. This processes the measurement data into graphics and uploads them to the public website of the appropriated district or town authority, where they are available for everyone to view. Of course, networks can be set up not only for cities, regions or countries. It is also possible to monitor a single kindergarten, transformer station or satellite ground station in this way. This example of the Serbian National Monitoring Network, run by the local regulator RATEL, shows how the measurement results can be presented. The The center of the screen shows the field strength versus time, with field strength shown in volts per meter or normalized to the limit value. On the right side, the measurement settings, such as the frequency range. Photos of the installation and the location of the area monitor on a map are also shown. So what are the major sources of radiation? Firstly, the low-frequency fields, which are dominant by the AC power supply with its 50 or 60 Hz fields. The magnetic field plays the main role here. Then there is wireless communication. This is often the focus of public interest with its medium and high frequencies. For these applications, it is usually enough to measure the electric field. But how are these fields monitored? The basic components of such a monitor are a basic meter with autonomous power supply and modem. A high-frequency or low-frequency probe can be selected depending on the application. The basic meter and probes are then weatherproofed by means of a protective radome. The configuration for monitoring the low-frequency fields for power supply networks, for example, is as follows. Firstly, the basic meter. Secondly, the sensor or probe for the low-frequency magnetic fields. And finally, the protective radome. That's your area monitor ready. The configuration for wireless communication is similar. Basic meter, high-frequency probe, and radome. If you want to monitor both applications at the same time from the same location, the Narda Area Monitor 8059 is a unique economical solution. Low-frequency and high-frequency probes can be connected to the basic meter at the same time. Both probes then simultaneously measure the particular field strength and pass this information onto the server. The two-in-one concept can be adapted as required. Continuous monitoring of low and high-frequency applications increase confidence and acceptance. It also results in lower investment, installation and maintenance costs. So, real savings for the user. The 8059 offers further unique adaptation, though, such as simultaneously monitoring of the electric and magnetic fields beneath high-tension cables. Narda provides both broadband and selective area monitors. What's the difference? The 8059 with a broadband probe is a typical representative of the broadband instrument range. It delivers a result that includes everything, the sum of all services. Regardless of whether it is long wave, medium wave, VHF, TV, cell phone, etc., everything added together gives one measured value. The different services cannot be separated. One number, one measured value for everything. Which service has contributed what to the result is unknown, but this is quite sufficient for most monitoring tasks. The 8059 can be equipped with band-selective probes, however. For example, fitting a quad-band probe allows monitoring of 4 bands simultaneously. Firstly, the sum of all services, including broadcast and cellular signals. And then, say, the 3 cellular technologies 3G, 4G and 5G separately. The various mobile communication services can thus be differentiated superbly. If you want more detailed monitoring, the 8061 is essential. The 8061 is a selective area monitor, what you might call a Swiss Army knife of area monitors. Of course, it can handle the same tasks as the 8059, broadband or band limited. But it can go into much finer details. The 8061 can determine the amount contributed to the overall result by a particular TV transmitter or cell phone provider. It can separate individual services with pinpoint accuracy and display each one separately. And, of course, the service of national interest to be investigated can be precisely defined by the system administrator. The 8061 is a chameleon among. Let's take a closer look at the Narda Broadband Area Monitor 8059. Here's a picture of the 8059 without the radome. Right at the top is a high-frequency probe. The measurement results from this are processed in the basic meter, saved if required, and then transmitted to the server via the built-in modem and modem antenna. Right at the bottom is a power supply consisting of a solar panel that provides continuous power through the day and charges the buffer battery at the same time. The battery takes over during night, enabling true 24/7 operation. Also, there are further communication ports situated on the underside of the power supply unit. A look into the power supply unit on the left shows the many different communication facilities. The basic meter takes care of the wireless communication, but all the wired services are found here: Ethernet, USB, RS-232, mainly for setting up and maintaining the monitor. The optical connector is particularly important. This allows communications with the monitor without the interfering effects of metal cables. As we know, metallic cables should be avoided if possible when measuring field strength. The basic meter without probe is shown on the right. You can see the two slots, one a micro SD card for the data memory and above it one for the SIM card. On the left is the antenna for the GPS receiver. 3 applications for the 8059. On the left, the standard application. 24/7 operation on rooftops, balconies, etc. thanks to solar panel and buffer battery. In the center, there is a version of the 8059 that has space for a large primary battery. It can be operated up to 8 months fully autonomously without any interfering cable in areas where there is no sunlight available, such as indoors. That's unique for an area monitor. On the right, installation with a magnetic mount on a car roof. This is the same area monitor as the one shown in the center, but now adapted for mobile use. Here, too, there are no interfering field-distorting cables. The optical cable can, of course, be connected to allow the observer in the vehicle to keep an eye on the field strength and to give the driver directions where necessary. And there are 4 variants for the AMB. AMB stands for Area Monitor Broadband, by the way. The main differences are in how the power supply is handled and the communication method used. The power supply can be either battery-driven or from solar energy. Battery operation means that the power supply lasts for up to 8 months of continuous operation from a replaceable commercially available primary cell. This means more than half a year of fully autonomous operation with a continuous supply of measurement data. Operation from solar energy means that the solar cell produces enough power during daylight to ensure continuous operation, as well as to charge up the built-in battery. This then powers the device during the night to enable true 24/7 operation. The monitor will continue operation even if there is an eclipse, or it is cloudy, or even if the solar panel is dirty or covered by snow. Even in complete darkness, the battery will last for 80 days and nights of continuous operation. So these are the 4 different versions of the basic meter. They can all be operated with the probes that will be now described and adapted to the application. Here is a summary of the application for which each probe is best suited. For example, if you want to monitor an Earth station and its satellite communication equipment, the EP1B05 is recommended. If this Earth station also includes links of above 18 GHz, then the next one in the line, the EP0106, is needed. This covers frequencies up to 40 GHz. All 7 of these probes are single-band broadband probes with linear or flat frequency response. The primary display units are volts per meter or amperes per meter. Here is an overview of the multiband and so-called shape probes. All these probes work in the high frequency range. The 3 and quad band probes can simultaneously measure 3 or 4 bands respectively. These are primarily mobile communication bands. The shape probes are frequency-weighted probes that give a measurement value displayed directly as a percentage of the permitted level of a particular standard. These probes are also capable of measuring the electric and magnetic field at the same time. So, what's special about shape probes? Traditional probes generally have a flat, narrow frequency response and are therefore sometimes called flat probes. The results from them are displayed in volts per meter or milliwatts per centimeter squared, for example. This is a very scientific way of expressing things which are not generally understood outside the scientific community. In contrast, the shape probes display the measured value as a percentage of the limit value. Percentages are well understood, and it's easy to see that the limit is reached at 100%. To make this clearer, let's use the example of bottled mineral water. As required by law, the contents are listed in detail on the bottle label. But these values are of little use for someone who simply wants to know if the water is suitable for preparing baby food. A scientist who can interpret the values would be needed to give a recommendation or advice. Or a simple logo printed on the bottle would be sufficient. So when measuring field strengths, displaying the result as a percentage of the limit value does the job of interpreting the results instead of the scientist. And there's another aspect that's important in EMF. The limit values can depend on frequency. Let's firstly look at a limit value that is linear. A common limit value is 6 volts per meter, which corresponds to 10 microwatts per centimeter square as shown here. If the measured field strength is exactly 10 microwatts per centimeter square, it doesn't matter what the frequency radiated by the transmitter is. It's always 100% of the limit value. So the measurement result from a flat broadband probe is enough to be able to convert the result into a percentage of the limit value. The actual frequency, which the broadband probe cannot inherently determine, is irrelevant to the evaluation. It's different when the limit value is dependent on the frequency, as with the ignored limit values. Let's assume a transmitter that is generating a field strength of 50 volts per meter corresponding to 0.66 milliwatts per centimeter square at the point of the measurement. If it is transmitting at 100 MHz, this would mean that it has exceeded the limit value by the factor of more than 3. If it is instead transmitting at 3 GHz, it would only be using up to 66% of the limit value, so there is still plenty of headroom. The frequency must therefore be known in order to make a correct assessment of field strength against the limit value. The result of a broadband probe with a flat frequency response is insufficient. In this case, a so-called shape probe is a better solution. It too is a broadband probe, and so does not know the frequency. But the frequency response is tailored, so that it is no longer flat but matches the frequency characteristic of the standard. When you use a shape probe, there is no need for tedious conversion calculation, as the result is shown directly as a percentage of the standard. And this works perfectly, even in multi-frequency environment. Here again is a comparison of the measurement results displayed by the two probes. Where the flat probe shows 0.66 milliwatts per centimeter square at 100 MHz, the shape probe immediately shows without converting the value that the limit value is exceeded by more than 3 times. Similarly, the display at 3 GHz for the shape probe straightaway shows that the limit is not yet exceeded. It would not be possible to make this assessment with a flat probe without knowing the frequency. This is the basic schematic of a flat probe. The output signal from the sensor, such as a dipole, is fed directly to this detector. This enables a particularly flat response. The shape probe schematic is different. There is a complex filter placed between the sensor and the detector, which corrects the frequency response to correspond with the frequency response of the standard. What appears simple here is in reality an extremely complex filter that has to reproduce the frequency response of the standard over several decades and up to 60 GHz, a real bit of high-tech. There are 4 different shape probes for the broadband Area Monitor 8059, which provide a display in percentage of the limit value depending on the standard at frequencies between 500 kHz and up to 60 GHz. The list of standard includes the limit value for the IGNIRP, the Canadian Safety Code 6 and the American FCC. Additionally, the probes capture the electric field and the magnetic field at the same time and can be used for the limit values both for occupational and for public safety. As already mentioned, independence from an external power supply is an important factor for an area monitor that measures electromagnetic fields. A power supply cable to a field strength measuring device is really a no-go. For one thing, it grounds the field strength meter, which should actually be suspended at zero potential and isolated. And it also acts as an additional antenna. The specifications stated in the datasheet will no longer be valid if a power cable is connected. Isotropy and frequency response data then become complete garbage. Also, devices powered by solar energy generally have a much lower power consumption. The ecological footprint is therefore clearly more positive, which should always be the case when environmental factors are being measured. Furthermore, the fully autonomous power supply reduces installation costs as no cable needs to be laid. And there are no energy bills either. There is, however, one other important reason why an autonomous power supply is indispensable for such a measuring device. Many area monitors are installed on rooftops and can therefore be struck by lightning. If they are electrically connected to the house wiring through the power supply, dangerously high voltages could be fed into the domestic installation and endanger not only any other technical equipment, but also the user as a result. In many countries, such installations are not permitted unless separate lightning protection measures are taken. Narda area monitors are therefore designed for 100% autonomous operation, for reliable measurement results, a better environment, reduction of installation costs, and the safety of people and equipment. A summary of the broadband Area Monitor 8059. Narda offers probes for up to 60 GHz for the broadband monitors, which cover all currently existing applications, including the planned 5G station in the microwave frequency band FR2. All probes have an isotropic characteristic and measure regardless of the angle of incidence of the radiation, as is required by many standards. Also, Narda supplies band-selective probes as well as so-called shape probes, which indicate measured values directly as a percentage of the limit value. The portfolio is completed by probes for electric as well as magnetic fields. The 8059 is configured for completely autonomous operation. It can also communicate wirelessly, so measurement results and alarms can be transmitted at any time. It can also use non-wireless services such as USB, Ethernet and, particularly importantly, optical cable for communication. The area monitors are, of course, ITU compliant, and there are now more than 5,000 installations across the world. The Selective Area Monitor AMS 8061. The 100 kHz to 6 GHz frequency range of the Selective Area Monitor 8061 covers all the currently installed communication frequencies. Like all Narda Area Monitor, it measures isotropically. This means independent of direction. Also, thanks to its built-in spectrum analyzer, it can be adjusted to practically any frequency band. 20 user-definable frequency bands are available for this purpose. The large solar panel and buffer battery mean that this area monitor is suitable for fully autonomous 24/7 operation. The integrated 4G LTE modem is used to transmit measurement results, reports and warnings. As with all Narda area monitors, it is supplied with a calibration certificate. Naturally, the measurements comply with the ITU K83 standard, and it can easily be integrated into web-based applications. Here is a typical example of integration into a web application. Alongside the display of the settings, location and corresponding photos, the central area is devoted to the display of field strengths in various frequency bands. In contrast with broadband area monitors, the frequency information is available from a selective area monitor. This means it can also compare any field strength measurement value against a frequency-dependent standard and show the result in units of field strength and as a percentage of the standard. The measurement value from the conversion are shown in two ways, as a table and as a bar chart. Other displays are possible, for example, field strength of each band versus time, and so on. The individual frequency bands can be defined by the user easily by using the configuration software supplied with the monitor. This example shows the FM radio service from 87.5 to 108 MHz. The associated measurement results can later be viewed in the web application. The basic meter of the 8061 contains a fully independent power supply from a solar panel and a buffer battery for nighttime. This ensures continuous measurement 24/7. The 4G LTE modem is used for communication, sending the measurement data and passing on alarms. USB or Ethernet can be used locally for configuration, for example. The air humidity can also be recorded thanks to its built-in humidity sensor. The integrated GPS module allows the measurement value to be linked to the actual location. The memory is in form of a micro SD card and can be removed as required. The 8061 can be adapted perfectly to the particular application by means of different antennas. The EHA2B00 antenna covers the broadest frequency band and can be used for most applications. Using area monitors on the move. Most area monitors are installed at fixed locations, so it is relatively difficult to extend or change the area that is to be monitored. The use of mobile area monitoring is very useful in this regard. The site can be reached without problems, and you can quickly react on the concerns of local residents. So-called drive-by tests allow you to monitor many more locations than can be covered by fixed installation. A combination of fixed monitors backed up with mobile monitors has proven to be very successful. The measurement field strength is correlated and safe with the actual position thanks to the integrated GPS receiver. This forms the basis for subsequent evaluations. The field strength can be shown according to position in various colors on the map. The magnetic mount for the area monitor can be fitted to practically any steel vehicle roof without damage. The vehicle and the measurement device remain electrically isolated from each other. The measurement values can be transferred to inside the vehicle through the optical cable so that they can be monitored during the drive and course correction made if necessary. The complete portfolio of broadband probes for the Narda Area Monitor can also be used for mobile applications. This means that probes from 10 Hz to 60 GHz are available. Consequently, even future applications such as 5G New Radio Frequency Range 2 are covered. As well as the field strength values, the temperature, humidity, battery voltage, speed, acceleration, data and time are also recorded. A complete record that includes all the relevant parameters. The measurement also complies with the requirements of ITU K113. Once recorded, the measurement results obtained can be shown in many different ways. Saving the results in GPX or KML format is ideal for importing them to Google Earth, for example. The measurement locations can be displayed on the map with the color of the indicated point corresponding to the magnitude of the field strength. Some project references. The Greek Atomic Energy Commission uses a national monitoring network to check the field exposure of the general public at relevant locations and uses the results to undertake local action when necessary. Mobile area monitors like these echo bands are also used alongside the fixed installations. Additionally, the Mobile Radio Communications Laboratory of the National Technical University Athens, the Radio Communications Lab of Aristotle University Thessaloniki, and the Computer and Communication System Lab of the University of the Aegean operate a network that measures and displays the non-ionizing radiation at further locations. The Fondation Bordoni has been operating a national area monitor network of more than 1,200 area monitors in Italy, the birthplace of area monitoring. Their policy of proactively informing the public has resulted in more than 50% fewer objections and protests against mobile communication installations. A small network of area monitor has been installed in Switzerland. The primary focus here, too, is to inform the public, and the latest project in Romania for ANCOM, the National Authority for Management and Regulation in Communication. So far, more than 5,000 Narda Area Monitor have been installed around the world. You can find links to further projects on the Narda homepage under Area Monitors. Safety and security with Narda Area Monitors. Safety. All Narda Area Monitors are calibrated, and Narda operates 2 of their own accredited calibration laboratories to the highest standards. This means that you can always rely on the measurement results from Narda devices. With unrestricted 24/7 autonomous operation, you can be sure that monitoring by Narda will always deliver results, whether the sun is shining or not. And thanks to this 100% autonomy, they can be set up completely isolated on any rooftop without any risk of inducing dangerous voltages into the domestic supply through power cables. Support is available worldwide in more than 150 countries to 55 sales partners right around the world, from Vanuatu to Tierra del Fuego. And of course, area monitors from Narda are compliant with the International Telecommunications Union (ITU) guidelines. Also, Narda has more than 20 years of experience in the manufacture of area monitors and more than 70 years in field strength measuring equipment. So far, more than 5,000 Narda Area Monitor have been installed and continue to deliver measurement results on time, day after day, for the protection and safety of the general public. Only Narda provides you with such a wide range of solutions for area monitoring. Whether broadband or selective, flat or shaped, electric or magnetic field, high or low frequency, Narda always has just what you need, but not at any price. Narda ensures that your investment stays within limits. Where else can you find monitors that can measure high frequencies and low frequencies simultaneously with the same basic meter? And they can be easily integrated into any website and keep a watchful eye on both installation costs and operating costs. So when it comes to area monitor, choose Narda. Annex. How to find the best location for an area monitor. Here are 3 possible ideas for finding a good location for an area monitor. First, where is an area of public interest, a sensitive location? This could be a kindergarten, school, university, retirement home, market, pedestrianized zone, and so on. Or where new base stations have been or will be installed, or where new buildings are sited near to existing stations, or where radiation is particularly high at so-called hotspots. These can easily be determined by spot measurements or by simulation. These methods can, of course, be combined. For example, a hotspot check made around a kindergarten. In this regard, the ITU states, the measurement point should be chosen so that it represents the highest level of exposure that a person may be subjected to, taking into account all possible sources of emissions. The maximum can be determined empirically through a quick scan with a field measuring equipment. Never forget that an area monitor is usually not used for scientific studies, but is there to inform members of the public about the actual level of radiation present. Involving the public in the choice of location is a further factor that can raise the level of acceptance for such measuring system. The special solution Selective Area Monitor AMS 8063. Transmitter locations with long, medium and shortwave transmitters are a special case. In contrast with the cell phone station that we find in our neighborhood, these transmitters are usually well outside urban areas and far apart. This is essential because of their purpose. They are not intended to just provide a mobile service for people within the next kilometer, or, as with the radio mast, to broadcast radio programs over the next 100 kilometers. They are built to send signals right around the world, if possible, or to reach a submerged submarine. This means that their output power is not measured in watts or kilowatts, but more likely in megawatts. And this means that the requirements for an area monitor are also special. Firstly, the frequency range and measurement range must meet the demands. And since the near field of such wavelengths extend a long distance from the transmitter, it must be able to monitor the electric and the magnetic field at the same time. Which automatically brings us to the Selective Area Monitor AMS 8063. This has all these features and has the additional bonus of selective measurement. It is, of course, isotropic, so it can measure fully autonomously regardless of the signal direction. Here is an aerial view of a submarine communications station in Sicily. The yellow square marks the transmitter mast of the 2 MW transmitter. Some buildings can be seen in the north. The red dots indicate the locations of Type 8063 area monitors. These monitor the field strength and warn staff and residents of excessive field strength. This was a short introduction into area monitoring of electromagnetic fields. There are more videos available on our YouTube channel. Thank you very much for watching and stay informed by our news ticker. Bye bye!